Look closely at any massive terrestrial data center driving today's artificial intelligence models. You will see heavy reliance on the local power grid and enormous volumes of fresh water consumed for evaporative cooling. The processing power required by modern AI is staggering. A single NVIDIA H100 GPU pulls 700 watts of continuous electricity. To solve these physical constraints, engineers are targeting the orbital pivot, migrating high-density compute into low Earth orbit. Space offers two distinct physical advantages. First, solar energy is abundant, with a 98% capacity factor unhindered by an atmosphere. Second, the vacuum of space allows heat to be rejected through infrared radiation. Star Nation Space Co. is positioned to lead this transition within the Canadian ecosystem, aiming to put off-the-shelf, high-performance AI hardware directly into orbit. But this introduces a severe engineering challenge. Operating a delicate 700-watt terrestrial processor in a radiation-heavy vacuum where traditional convection cooling does not exist requires entirely new design architectures. Solving these thermal and radiation hurdles moves AI infrastructure away from a geography-constrained terrestrial model and builds a sovereign orbital alternative. The physical reality of the space environment presents a stark paradox. It offers uninterrupted solar power, but it has zero air. On Earth, server racks rely on convection, fans pushing cold air across hot metal. In a vacuum, convection is physically impossible. This 3D model isolates an NVIDIA H100 GPU inside a microsatellite chassis. A chip like this outputs an intense thermal load of 700 watts. Star Nation's thermal management strategy strips away the terrestrial fans, replacing them with a liquid-based heat pipe system. These liquid lungs attach directly to the silicon baseplate, continuously drawing the severe thermal load away from the delicate processor. The pipes then transport that heat outward to a series of expansive, lightweight aluminum radiator panels on the exterior of the satellite. Since there is no air to carry the heat away, these panels reject it by emitting infrared radiation directly into the black void of deep space. That continuous radiation handles baseline temperatures, but AI processing is dynamic. Complex tasks create sudden, massive heat spikes that the panels cannot expel fast enough. To manage these spikes, engineers integrate a phase-change material directly into the cooling loop, specifically a reservoir of paraffin wax. This wax acts as a thermal shock absorber. During peak compute periods, the sudden burst of heat melts the solid wax into a fluid, absorbing the excess energy without raising the chip's core temperature. Later, when the satellite passes through the shadowed, cooler portion of its orbit, the wax slowly resolidifies, steadily releasing the stored heat to the radiators. Vacuum thermal management requires an architecture built on liquid transport, phase change absorption, and continuous infrared radiation. Once the heat is managed, orbital hardware faces a second, equally severe threat: the constant bombardment of high-energy cosmic radiation. This diagram illustrates a microscopic view of a silicon logic gate. When a charged particle strikes it, it causes a bit trip, flipping data from a 0 to a 1. In a complex AI model, a single bit trip can crash the system. Traditional aerospace engineering mitigates this by using heavily shielded, rad-hardened chips. But these specialized components are typically several generations slower than modern AI processors. Star Nations takes a different approach. They use standard off-the-shelf H100 chips surrounded by targeted, lightweight aluminum shielding blocks to stop the weakest particles. Custom software provides the primary layer of resilience for high-energy particles that penetrate the aluminum shielding. Before launch, identical terrestrial chips are exposed to particle accelerators on Earth to precisely map out their specific physical failure points. Armed with this mapping, the onboard software continuously scans the architecture, identifying and correcting bit trips in real time, the exact moment they occur in orbit. Shifting the burden of radiation resilience from hardware into intelligent software makes it possible to deploy the fastest terrestrial AI chips directly into space. With the individual satellite node engineered to survive, the next step is designing a network architecture that makes the system functional over a specific region. Global telecom providers build mega constellations, requiring thousands of satellites. Star Nations utilizes a much smaller, highly targeted 4-satellite architecture. Placed in a non-geostationary low Earth orbit, this tight cluster provides continuous, high-frequency coverage tailored exclusively for mission-critical operations over specific geographic zones. Maintaining this low altitude minimizes the physical distance the signal must travel, which drastically reduces latency. Near-instantaneous response times are mandatory for night-edge processing, especially when tracking moving targets, like fast-spreading wildfire fronts or active maritime shipping routes. The nodes communicate using inter-satellite links, specialized lasers or radio transmitters that create a continuous path for data packets. A massive telecom network requires complex routing algorithms to connect thousands of dispersed nodes. A 4-satellite network simplifies these links, creating a stable, closed relay system. Processing data at the orbital edge bypasses the bottlenecks of terrestrial fiber optics, delivering results directly to local ground stations. This targeted architecture directly aligns with the strict procurement requirements of primary government clients, specifically the Department of National Defense. For defense agencies, hardware capability is irrelevant if the processed intelligence is routed through foreign servers and becomes subject to foreign data laws. To ensure an unbroken sovereign loop, Star Nations is partnering with ThinkOn, a 100% Canadian-owned cloud provider. Data downlinked from the orbital nodes never leaves Canadian legal jurisdiction. This sovereign loop is finalized on the ground. By launching domestically from Spaceport Nova Scotia, the entire supply chain remains under national control. The viability of deploying these heavy server racks depends entirely on launch economics. This chart tracks the historical drop in orbital launch costs per kilogram. The tech industry has established a clear benchmark. Once the cost to launch drops below $200 per kilogram, orbital compute achieves unit economic parity with terrestrial data centers. Current medium-lift rockets have brought costs down significantly, and upcoming fully reusable heavy-lift vehicles are projected to push prices below that $200 threshold by the end of the decade. The combination of secure sovereign cloud architecture, domestic launch capabilities, and plummeting lift costs converts this engineering model into a scalable defense asset. The Star Nations operational roadmap outlines clear steps to reach that benchmark. As seen on this timeline, the immediate focus for 2025 and 2026 is the rigorous hardening and validation of the H100 payload at elite testing facilities, like MDA Space's David, Florida laboratory in Ottawa. Following validation, the 2027 phase targets the manufacturing, systems integration, and final flight qualification of the 4-satellite constellation. This culminates in the ultimate milestone, scheduled for the fourth quarter of 2028. The launch of the operational shell directly from Canadian soil. Migrating to orbit removes the land use and power grid constraints currently capping terrestrial AI growth. Disciplined engineering and terrestrial testing have proven that high-performance GPUs can thrive in a vacuum by relying on liquid heat transport and software-defined radiation resilience. Orbital data centers represent a functional evolution of digital infrastructure. The vacuum of orbit serves as the physical engine for sovereign computing power.